warm welcome to all in the Big Data Conference on the Machine Learning Track, and I will be your moderator. So let us start the session by introducing you to our speaker, Oliver Gindele, and he's the Chief Innovation Officer at Datatomic. His passion is to solve real-world challenges of applying deep learning techniques. And in today's talk, he'll be talking about ML in production, serverless, and painless. So I invite the speaker to present himself.
Thank you very much, and welcome and good morning to everyone to join this session in the machine learning track. In this session this morning, I'm going to talk about machine learning in production and some serverless and painless approaches on operationalizing machine learning pipelines. I'll walk you through a case study that is rather simple, but still highlights a few of the concepts that we think about when putting ML into a production environment. But I also want to expand on this and show some of the newest tool sets, specifically within the cloud computing world, that can help you productionize machine learning models. Before we jump into the subject matter, a few more words on introduction. As mentioned, my name is Oliver Gindele. I'm Chief Innovation Officer at Datatomic, and I've been with Datatomic for about 5 years. My previous background has been physics and computational physics, especially, where I worked a lot in high performance computing. In case you don't know Datatomic, we are a boutique consulting firm that specializes on providing data services and data products in a range of industries, mostly media, retail, and telecommunications. And in a nutshell, we do all things data and work very closely with Google Cloud Platform, where we work with some of our customers to build innovative and novel data science use cases. And I'll give you an example on that in the case study later. I want to now start with a question and then give you my opinion on an answer to this. But the question is, why is moving machine learning models into production so hard? One way to answer this and to think about this is if you look at the workloads that we have to deal with when we productionize machine learning models. And often the perception is that AI or ML workloads all evolve around building a model, or building a model is the single most important workload. But productionizing AI is much more than building a model. And I'm now not talking about these 80% of data science work is data wrangling or data cleaning. I'm talking about all the other tasks and workloads that you need to consider when you want to build robust and reliant production services that serve and bring machine learning predictions to customers in internal business. So what do I really mean by that? I want to show you the reality of our workloads here. And that's just a list of examples. I'm not going to go into detail, but I want to show you the contrast between the reality of what we believe is the need for AI workloads and tasks and the perception, which is evolving around building a model. So besides the model build, there's of course task and consideration that goes towards the data and the features, but there's also many other things such as versioning, building APIs, thinking about retraining and storing data and models. There might be some elements of monitoring of the performance of the model, but also monitoring of the service. You need to consider and discuss upgrade paths, security, and potentially also testing the effectiveness of the model in production. Lastly, the whole stack and the whole pipeline needs to be maintainable and manageable in the future as well. So there's a lot of these tasks that come into building a production service, and many of these actually sit very firmly within the realm of software engineering, software development, or DevOps and operations in general. And this is really what brings us into the realm of MLOps, machine learning operations, because these two fields, machine learning and operations, overlap when you want to build production services. So let's put this into a slightly different perspective. And I want to bring this into perspective of the overall machine learning process. And there's a few steps that we usually go through when we build a machine learning or data science use case. The 5 steps that we think are key start with discovery, where you might have a crucial and important look at the data and do exploratory analysis. You then move on to the second stage, the pilot, where you want to quickly trial and build machine learning models and test if they're suitable to actually deliver to a business case. If a pilot is successful, you want to move on to the stage 3, 4, and 5, which are deployment of a machine learning model, monitoring, and hopefully optimization. And in today's session, I want to talk more about the steps 3, 4, and 5, which really are about the operationalization of the machine learning model. And this is where I believe the whole concept of MLOps really puts the weight in. So there's, of course, very much importance in the discovery and pilot phase to establish a use case. But once proven, a lot of work will go into deployment and some tasks and workloads associated with that. A lot will go into monitoring, and this is also where you can leverage some existing infrastructure. And then potentially there's also room for optimization, depending really on the use case as well. But you now see some of the tasks I showed on the previous slide find themselves here again in some of the concepts as well. And the world and the realm of MLOps really adds benefit to stage 3 and 4, but potentially also to the stage 5 here. So you see, productionizing machine learning model becomes difficult because there's a whole range of tasks that need to be considered. And these tasks might also not be necessarily where data scientists are most comfortable. So I want to show you now some views in how to achieve operational machine learning models. And initially as easy as possible with maybe taking some shortcuts, but then expanding on that and bringing into view and machine learning ops platform that can really deliver against all these requirements here. So let's start simple with some tactical level of AI maturity or MLOps maturity. And that's probably something you're quite familiar with if you're a data scientist or machine learning practitioner. And it all starts with some offline data, some training data at the top. And this is the blue cylinder here. And we then quickly move into these orange steps here in the middle of the diagram, where we do data extraction, some data preparation, and potential feature engineering. There's a step of model training, of course, where we fit the model to the historic data. We want to evaluate and validate the model output, but ultimately, maybe one-off, we want to export a trained machine learning model. And we can export this into some sort of model registry. And this is really the boundary where often the data scientists will work. And then you see this line, a divide towards the ops, where now the machine learning model gets built into a service. And this might be just a simple service relaying the predictions to customers or the business. So this is quite an easy manual and ad hoc way to build some machine learning operations and bring predictions to customers. This works well, especially if you have hands-on data scientists that can update models and go through the orange steps again if the model needs an update. And also if you have a team that's very happy to just take on a model binary and build a service around this. So this can work well in practice, but where we want to go to offers a bit more capability and more of the thinking of traditional software development, where we want to move towards continuous deployment and constant monitoring of data products. So this is now what we call a transformational view, where we see there's a few more elements, but don't be shocked. I'll build this out a little bit now and then get back to this later. But what I want to highlight is that now we consider many of these operationalization tasks I introduced at the beginning and try to build this into the architecture. And if you look at now the pipeline steps here in the middle, still these orange steps, they become a bit more complex because we add validation on the data, but we also add validation on the model. But in essence, they stay the same. However, what we might also want to do is add an element of automation where we can go with a process through these steps at any time through any trigger we want to produce new and update models. For example, when we have new training data or we have other considerations that might change a model. Models obviously are still stored in a model registry, but this is then where it gets combined, and this is what you see on the right-hand side, with a CI/CD process. So instead of manually updating a model in a production server, we actually want to have a continuous deployment process that will potentially have updates from this prediction service, takes new model binaries in, and pushes them into the production environment based on some requirements. What we also want to add is the performance monitoring. So we want to monitor the production service that it can really deliver the predictions of the ML model at scale and with the requirements, for example, around latency we need. And if there's some mismatch, we might want to take some steps and actions away to rebuild models or to rebuild and change, for example, the service code or the data. So we can use the performance monitoring on the service, on the key metrics there, but we can also use it on the accuracy and the performance of the model itself. And if there's changes needed there, we obviously need to go back potentially to the drawing board, even to the data. And that's what you see all the way at the top here of this diagram. So within a fully fledged MLOps environment, you also want to have a space for experimentation at scale ideally, that combines the data analysis and the model analysis, where data scientists can experiment and produce new models, but also updates and experiments on the service that actually serves and calls the ML models or combines multiple ones together with business rules can be experimented with. So keep this in mind. I know there's quite a few elements on here, but we'll touch upon some of these throughout this session. So now I want to take a step back and bring back to mind this tactical view of achieving some basic level of machine learning operations. And I want to put this into context of a real case study. So I want to talk about a simple case study, and that's been a project we've done for Lush Cosmetics. In case you're not familiar with Lush Cosmetics, they're a global cosmetics retailer, and they are probably most famously known for their bath bombs that you see on the background here. So they make many cosmetics products. They're all handmade and sell them in stores across the world. As a company, they are very ambitious to also drive to more sustainability. And one project they drive themselves is reducing the plastic packaging they have in stores. So they want to get rid of the packaging that comes with these soaps and bath bombs, but this brings up another challenge. If you reduce or remove completely packaging in the store, you also remove label information. And you see this on the shelf here. You have items, you can obviously add some signs and labeling onto the shelves, but the products themselves will miss potentially crucial information that the customer would want. This is particularly important if it's cosmetics, because people apply these products to their skin and take it in their bathtub. So to allow customers to still have all the relevant information, Lush had the brilliant idea to use everyone's mobile phones as a digital label. So how does that work? You might go into a store and you see all these products stacked up on the shelf. Now you can take your phone, and in absence of any label information, you can take a picture of the product, of the soap bar, and a machine learning model, computer vision model, will recognize the product and pull in all the relevant information to you. And this is available in what Lush calls the Lush Labs app, and you can use this in store and at home. So we worked with Lush to really make this a reality, and they had an initial prototype ready to do this image classification in their mobile app. But their first model was quite hit and miss. It would only have an accuracy of around 50% and was only available on iOS devices. So we worked with them to make the model available and this service available for iOS and Android, and to improve the performance. But also more importantly, the Lush app developers were not machine learning experts. So they needed a process, a machine learning pipeline in operation that can produce new machine learning models when they update their products. The products continuously new products are introduced by Lush, so they need a way to produce new machine learning models that would reflect these updates. And we worked with them to design really hands-off process so that they can create new training imagery easily, upload this into a specific location in the machine learning pipeline, and then the pipeline would automatically produce new models for them to bake into the app. But let's talk about the computer vision task and the machine learning model for a minute. The model we used was an image classifier. We used transfer learning and based it off a convolutional neural network called MobileNet V2. Initially, you think computer vision, that might be a relatively easy or solved task these days, but this actually has really some complications here. First, the computer vision task is not that trivial because all the products are handmade. So they're never perfect. There's some defects, or you might use them at home, where obviously if you use half a soap bar, it won't quite look like the day you bought it. Secondly, a lot of their products are very similar. So I showed you these bath bombs. They have many of these bath bombs in different colors and slightly different shapes and gradients. So they all very much overlap a similar image space. So the classifier needs to be quite sensitive to that. This is not distinguishing between a chair and a car. This is distinguishing between very similar products. And also this needs to work in very different lighting conditions. It needs to work at home and it needs to work in the store where the type of lighting and the way you take pictures might be vastly different. Also, we have to consider that we want to run this as a machine learning model within a mobile app. So storage space and performance of mobile chips are limited. And this is why we resorted to do transfer learning on top of a already mobile optimized neural network architecture. To solve these challenges, we did very careful data selection and image augmentation. This was a huge driver in performance of this model because of the issues I mentioned, that the product space is just very similar. So we paid a lot of attention to that. We tweaked the neural network architecture as well and did some extensive hyperparameter tuning. But what we ended up with is a model that was initially really just hit and miss to something that really reliably could recognize the many hundred different products. And there was also extensible to new product and product categories overall. So now we have this model and we built this all in TensorFlow, and I'll mention a few more things on that in a minute. But let's now try and work on putting this into a pipeline that can produce new versions of this model whenever Lush has a new product and new training imagery. So a quick reminder, for that, we want to consider a few points. We want to have some sort of continuous delivery. We want to actually make Lush able to ship new models like normal software, and we want to bring in some levels of automation as well. Overall, this really should reduce the development cycles and take off a lot of the manual work and going manually through steps where needed. So if you now think of technical tasks in a pipeline, and also back to the architectures I showed you before, we have a few tasks to take off. I mentioned pre-processing and data augmentation is important, so we need a task to pre-process the images. We need some automated training and evaluation because you want to spit out new models as new training data comes in. It's crucial, thirdly, that we monitor and track model performance, because if new data would, for example, degrade the performance and the accuracy of the model, we don't want to release this. And lastly, there needs to be some stage of storing and versioning the models, again, in order to revert to older versions or to also do some analysis of the whole machine learning project as a whole and to have some guidance on how to improve performance in the future. As we spoke a little bit about TensorFlow and mobile models already, we put this into a simplified view where we have a TensorFlow model at the center. So when we started now working with Lush and tackling this problem of building better models that are accessible on Android and on iOS, we knew we start with training images all the way on the left, and we knew we need to have a trained model that can be baked into mobile apps. To enable that, we choose TensorFlow and TensorFlow Lite, because TF Lite is this portability layer that comes with TensorFlow that allows for straightforward deployment into mobile apps and also allows for some tricks and methods to reduce size while keeping performance of models. So this seemed to be a perfect solution to build high quality image classifier that recognizes these different cosmetic products and also have a very small model binary that can work in many, many different types of user mobile phones. So now we just need to fill in the gaps here. There's still some question marks on how to approach this pipeline overall. But let's take another very high level look of the pipeline. We basically start from the same original point, which is the image upload, and now work completely with Google Cloud Platform to make this a reality. So we do image upload to Google Cloud Storage, and basically we have a folder for each product type that will then host several training images. There's an immediate step that follows, which is data preparation. That's succeeded by a step of machine learning, and then we can serve the app on mobile devices. So that simplified view, let's really drill down into these two boxes of data preparation and machine learning. Data preparation first. As I said, we start with just normal imagery that Lush takes in a specific rig that takes pictures of their products from different angles. And we want to have a decent quantity of these images as well. The first step, what we do on a processing level, is converting the images to TF records. TF records is TensorFlow's preferred format to store training, but also serving data, and it yields some nice performance benefits if you do training at scale. Because we want to have this whole pipeline as hands-off as possible, we choose a serverless, completely managed service to do this conversion, and that's Dataflow. That's a managed service of Apache Beam, and it can do this conversion very quickly and in a very scalable way with no infrastructure to be built or maintained. Once we have the TF records, we can split the data into training sets and evaluation sets, and we store them again in Google Cloud Storage. Now, the many parts of data augmentation, not going into detail, but there's quite a few actions that happen here, as in randomization, flipping, zooming, cropping, and changing of color profiles and saturation. And we do this in TensorFlow with TensorFlow functions in Google Cloud's managed service AI platform, or it's now called Google Vertex AI. So again, this is really a job we submit to the cloud service. There's no infrastructure and no management at all. This is a completely serverless data augmentation task as well. So now we have the data ready to actually train the machine learning model. So we're going to go and I'll walk you through the next block of this pipeline now, the machine learning part. The first step is the actual model training now that we've prepared data. And again, we do this in Vertex or AI platform as a training job. This spins up a few instances, virtual machine instances under the hood that we don't need to manage or deal with in any shape or form. And we can easily do this at any scale we want, also to do hyperparameter tuning and evaluation, for example. Once the training job is done, we can store some metrics that we calculate. These are metrics of performance of the model on the held out evaluation set. And for simplicity, we store this in BigQuery data warehouse, again, of course, serverless, and it just allows us to quickly and easily store these metrics. Now we want to maybe have some level of automation or at least validation of the model, where there might be a task to check whether the model performance is good enough. If it's above a certain threshold, we move on to the next step. If not, then we might want to flag this or actually stop the pipeline at this stage and consider dive into some analysis of what went wrong with the model training. This could happen if some new training data has very many training images, for example, and the performance degrades for some reason, and there's some potential influence also of other product categories and classes that changes the performance overall. Assuming everything goes well and the model accuracy is above a certain threshold, we can, however, happily move on to the next step. The next step would be conversion of the model, which is a TensorFlow model, into TensorFlow Lite. And this is, again, a job we can easily do in AI platform. You can actually also tag it onto other jobs. And we export this model to TensorFlow Lite, and we then store it in Google Cloud Storage, blob storage, as a model version. You can use naming and metadata to do the versioning properly here. But of course, it's a very basic way of tracking different types of models. Before we put everything together, I want to mention a few more words on the model training. I told you we use TensorFlow in AI platform, and that's a really neat way because you can scale the TensorFlow training, evaluation, and hyperparameter tuning jobs very easily. It's completely serverless and fully managed, and also allows you to do distributed training, which is, again, for hyperparameter tuning, very useful. You can run the same code that you might develop on your local machine and run it with no change at all. So it just runs TensorFlow code as jobs, and you can easily attach a GPU or TPU, multiple ones across many nodes if you do like and have the money to accelerate your training. So this is really handy service, and it's getting built out more and more to also build out managed model versions that you can query in the service that's now called Vertex AI. I mentioned we use TF Lite, or we export it to TF Lite, and that's very neat because it allows to use some facilities to reduce the model size. This usually comes with a slight hit on the performance, but you can do some experiments, which we did, to really find a good trade-off between size and classification accuracy. One thing we did, amongst others, was full integer quantization, and this allowed us to have a fully trained neural network model based on the MobileNet V2 architecture that's only 3.5 megabyte in size. So this is really nice because if you're on a phone and you need to update to a new ML model on a weekly basis, you don't want to download lots of neural network weights onto your phone every time, as in customers don't want to have huge app updates. And also small size, fewer weights mean that the image classification takes milliseconds rather than seconds. I also mentioned this quick and easy way to store the metrics in BigQuery. I'll just give you a rough example of how such a model evaluation or model metadata store could look like. We have just simple rows where we have a row ID, a run, and of course a timestamp. There might be some information on the task that the model performs, as a number of classes. And then we keep track of all the metrics we would like to store and inspect. So there's accuracy, recall, the F1 score. And now basically we can just set up some rules. We can do analysis on the experiments as well. But if the F1 score is above a certain threshold, we progress with the next steps. If not, we might want to really dig into the specific training job and see what went wrong. So we covered now all these elements that we think makes this pipeline and really delivers against the needs that Lush has to build and produce new ML models as hands-off as possible. And if you put this all into one bigger architecture, it looks like this. So I'll briefly walk you through the steps again. Again, we start with an image upload, and what happens here in practice is now if Lush has a new product, we would ask them to take 30 or more images and move them into Google Cloud Bucket. If you move them into a folder and label that correctly, this whole pipeline will be triggered because it recognizes there's a new class to predict. The first part of the pipeline is then the conversion to TF records. Again, we do some splitting of training evaluation and data augmentation, all in the what we call data preparation stage. Move then quickly on to the machine learning stage where we train and evaluate the model, and if everything goes right, we export it as TF Lite. So what we end up with at the end is a newly trained machine learning model as TF Lite version in Google Cloud Storage, and the Lush app developers can now take this and move this into either Android or iOS app. So there's one crucial element that we haven't covered yet, and that's how we stitch all these tasks together. And this is something I introduced now at the top here, where we use Apache Airflow as an orchestration engine. So Apache Airflow, it allows you to define all these tasks as simple Python code and then set up the dependencies between. So we have one single pipeline that goes through all these steps, maybe with the check on the evaluation metrics or the check on training data that I mentioned before. Google Cloud Platform offers an easy way to run Apache Airflow with a product called Cloud Composer. And again, this is fully managed and serverless as well. So now we have the whole pipeline in place, and we have a process that triggers and guides us through all the steps. So we can quickly recap and look at what we've actually achieved. So we built a serverless ML pipeline that's completely hands-off and on Google Cloud Platform. We were able to make this computer vision classifier available to Android and iOS at the same time. And we also unlocked a huge improvement on the model performance. If you want to try this and you're a Lush customer just curious, you can download the Lush Lens app, and it looks like on the right-hand side here, where you basically just open the app, it uses your camera, and it will recognize the product and then pull in the information you would need, such as allergens, price, or product name. So basically, you have a digital label that will help you in the absence of any plastic labels because they will be removed in the store. So this was now an easy way to achieve this serverless ML pipeline and build production-grade machine learning models. And I want to now look back to the beginning where we thought about the MLOps operations. And we actually ticked off most of them with this simple case study. So we have our orchestration. We can scalably train and build ML models. We have a little bit of monitoring, hence the brackets. We have a little bit of data validation. There's some model versioning and governance, again, bracketed, and a little bit of continuous integration and deployment, but there's still some improvements and some desire to go a bit beyond this. So with that in mind, we achieved this initial tactical solution, and it was actually quite easy to build within Google Cloud Platform and these fully managed products. But I mentioned, and you saw, we have some tasks only ticked off with brackets. We want to improve on that. So let's think again about this transformational view. And for that, I want to introduce two key products that we use quite frequently and more that really allow you to build a much more complete MLOps platform. Benefits are that we bring in deeper integration and continuous development. We bring in more levels of data and model validation. And it also allows us to not custom build an MLOps pipeline for each use case independently, but build a whole platform that can host a series and many different ML pipelines in parallel. The two products And open source softwares that I want to introduce here are Kubeflow, which can really host a lot of the tasks you see on this architecture, and TensorFlow Extended, which kind of sits here in the middle of this diagram, which is really concerned about the machine learning, the pipeline that surrounds the immediacy of the machine learning model. And I'll get to that in a minute. But let's start with Kubeflow. Kubeflow is an ecosystem that allows you to do machine learning on Kubernetes. So if you're already user or familiar with Kubernetes, you know you can obviously run and orchestrate any sorts of jobs and services and scale this out across your clusters. That could be in the cloud or on-prem or hybrid. Now, Kubeflow is the toolkit that brings in a lot of the machine learning capability and a lot of the familiar frameworks to do machine learning specific tasks scalable on Kubernetes. It brings in the usual suspects such as PyTorch, scikit-learn, and TensorFlow. It has a lot of its own tooling, which I'll get to in a minute, and it also leverages some of the Kubeflow ecosystem around orchestration or around monitoring of services and applications. And as I said, you can run this wherever you can run Kubernetes, and this might be actually locally, this might be on cluster, this could be an on-prem data center, or this in ideal cases, some cloud implementation of Kubernetes. One particular aspect I want to talk to is Kubeflow pipelines. You saw this whole operational ML pipeline we built for Lush. Kubeflow pipelines offers a service and an SDK that allows you to build similar chains of tasks to really work towards updatable, maintainable machine learning products. So the main objectives of Kubeflow pipelines is to have this orchestration. We've done this before in Airflow, but you can use Kubeflow pipelines with that. There's easy experimentation, so you can scale out and really utilize a Kubernetes cluster with GPUs, for example, or many nodes to scale and track your experiments. And whatever components you build, as in training tasks, validation tasks, model blessing and exports, you can build as Docker components and easily share them within your organization and reuse them. So each task within a Kubeflow pipeline will be a Docker container. There's multiple ways to build that, but it allows also seamless collaboration between data scientists, ML engineers, and DevOps engineers to build out complete ML pipelines. So the components that make this possible is the orchestration engine that uses Argo under the hood. There's even a UI, which is very useful to track experiments, where you can visualize model performance and output. And as I said, multiple ways of building these tasks as Docker containers. And one will be using a Python SDK. Others will be to just build the Docker files from scratch if you'd like to. So this really offers a lot of flexibility and generalization to build many of the tasks around continuous deployment of ML models. If you're more concerned about building reliable and robust ML models and you're already using TensorFlow, I want to bring TFX into the picture. So TFX is an extension, as the name, of TensorFlow, and it really comes with a whole host of tools and schematics to build validated and robust machine learning models. So we'll help you with validating the input data, with scaling and validating the models, and also with pushing them into production services. As I said, it comes with many tools, so you can drill down into model analysis, you can validate infrastructures or different data drift within different stages of the ML pipeline. So it's very opinionated around TensorFlow and very focused on the model lifecycle itself, but I think it's a great tool to put into your MLOps arsenal as well if you're already using TensorFlow. So before we close out, I want to give you a few takeaways. We saw that actually building a complete custom machine learning pipeline is not that difficult at all. If you want to start with a simple tactical view of operationalizing machine learning models, you can easily do this by utilizing off-the-shelf tools that some of the cloud vendors, such as Google Cloud Platform, already offer. This is nice because often they're fully managed and battle tested, and it will easily allow you to build a tailored ML pipeline. If you do desire much more consideration around validation and continuous deployment of ML models, or running many ML models in parallel, many use cases, you want to invest in building out the more fully fledged MLOps platform. And this is really where Kubeflow and TensorFlow Extended will find their place. With that, I really want to thank you for your attention. I see we getting close to the end of the session, so we can move over to the Q&A, where there's also been some questions posted in the chat here. So thank you very much again, and we'll move over to Q&A.